Thanks for coming today, everybody here in person and also those of you attending virtually. We're very excited to be welcoming Ian McGregor, who's a newer postdoc here at Cary. He's going to be telling us a little bit about the work he's done in the past and also some of the work that he'll be doing in the future. Before I introduce Ian, I also wanted to note, for those of you here at Cary right now, there is a lunch after this in the lunchroom over in the TESB, and there'll be a happy hour at 4 if you wanted to have time, either of those events, to talk to Ian a little more about his work or chat with each other. So Ian has had a fascinating path to us. He originally did his bachelor's at Berkeley with a focus more on conservation and natural resources. And after that, sort of staying on that trend, went to Oxford and did a master's there with fieldwork in Gabon, studying some fire effects on savannas and forest boundaries. That master's also was in a program focused a lot on science policy. After returning from that, Ian then went and did an internship at SCBI, the Smithsonian Conservation Biology Institute, where he did a lot of different things, including some forest dynamics work, forest plot work. And then after doing this field research, Ian realized something he really wanted to add to his skill set was a lot more on the programming end, ended up doing his PhD in geospatial analytics at North Carolina State University, where a lot of his work, which we'll hear about today, focused on multi-sensor data fusion, which if you're familiar with remote sensing work, that's sort of a elusive skeleton key type problem that people have been pursuing, try to integrate all these different types of data to answer one specific question. So really excited to hear a little bit about that. And I encourage you to have time, chat with him about things. He's also a very varied person with tons of different interests and skills, and a fun person to talk to. So with that, I'll allow Ian to continue.
Thanks, Evan. So hello, everyone. Welcome to the seminar. As you can see, advancing near real-time deforestation monitoring via multi-source remote sensing data, landscape processes, and end-user contributions. And this is, of course, PhD research, but I'll also speak briefly about my work here at Cary. So some little bonus lightning content, I think. Okay, so let's get going. So just a little bit about me, as Evan said. So I'm originally from California, so a lot of my environmental education was originally from this state. I grew up going to the beach, but then I also looked at and worked in deserts and wetlands. And then for my bachelor's, I got to see more of the central coast and north coast of California. So California has really shaped how I approach things. And so I supplemented my natural education from the state with my formal academic education, as Evan mentioned, first at Berkeley, then at Oxford for a master's in policy, and then most recently my PhD, which I'll discuss further. Now, I should say that even though my PhD research focused somewhere else, my physical research was conducted in Raleigh, North Carolina. And as such, I want to acknowledge the Tuscarora and Catawba tribes as the original inhabitants of the land, that NCSU as a land-grant institution is built on land stolen from these indigenous tribes. Okay, so let's get started. And we are going to meet Allie. Now, Allie is a manager of a tropical protected area system covering a variety of habitats that collectively is home to endangered biodiversity and forest types. Now, she's recently received notifications about increasing deforestation around the park. And field staff have noted that it happens along new roads and in flatter areas, but they haven't been able to incorporate these patterns into the detection. Now, Allie knows that if they can catch loggers in the act or predict when and where deforestation can happen, then her team will be able to ask the government to intervene. But their ability to do either of those things is lacking. And she only has a small team, as you can see, from multiple protected areas with a limited budget. Now, what Allie needs is a way to easily monitor these large areas, even with the small field teams. So what Allie needs is remote sensing. Now, remote sensing is, or satellite remote sensing, is the process by which we have sensors orbiting around the Earth in order to glean information about it, from monitoring forests to mapping floods from storms to tracking animal migrations, for example. Now, there are two primary types of sensors that we use for this. And the first is an optical sensor, which records reflected radiation from the Earth as it orbits. Now, specifically, they're called optical because they can kind of see like us and make true color images, which many of us have seen before. Now, with these sensors, we tend to monitor forests by seeing how green the canopy is. And the most common metric for this greenness is an index called NDVI, which is a combination of the red and near infrared wavelengths. Now, the index ranges from -1 to 1, with the lower end representing dead vegetation or dirt, and the upper end representing healthy vegetation. So to illustrate, an evergreen forest has high NDVI, little fluctuation over time. There's little seasonality there. Whereas a deciduous forest has high variability with that seasonality. So one other way to monitor the Earth is using microwave sensors, especially synthetic aperture radar or SAR data. Now, in contrast to optical sensors, these microwave sensors directly send out energy toward the Earth and then record that reflected energy as it comes back. Now, in ecological remote sensing, we focus on SAR sensors with longer wavelengths because we value them for their ability to see through things. For example, SAR data can be used to identify ongoing flooding from an active storm as it's happening. So thus, unlike with optical sensors, we can get usable SAR observations regardless of clouds and time of day. And these types of sensors are part of a long history finding deforestation using remote sensing. However, it used to be more difficult and expensive than it is today. Prior to 2008, satellite images were hard to come by, and thus deforestation studies were often done by image differencing, where researchers compared a before and after image to see where and how much change occurred. And that all changed in 2008. That year, the USGS decided to make all satellite imagery from the Landsat sensors free and open to the public. And this was revolutionary because it instigated the shift from image differencing to time series approaches. And in a time series analysis, we can see persistence of change over time, such as with NDVI, and we can then see long-lived changes, which we can't only see with 2 images. So now we can use all of the possible imagery we have and model how aspects of a certain area fluctuate over time. And this animation, for example, is NDVI over the course of a year. Now, of course, remote sensing can cover large areas on the ground. So to be computationally efficient, we can partition them into individual pixels, similar to a computer monitor. Now, Landsat, for example, has 30-meter resolution. So each pixel is 30 meters by 30 meters. And we can then run a change detection analysis over each pixel simultaneously. Now, many studies have developed algorithms to automatically find anomalies from pixel-based time series approaches. So let's go back to Ali for a second. Now, Ali has been trained to use one of these models, and it's helping. But she notices how deforestation events can occur pretty quickly, sometimes within about 2 weeks. Now, a single sensor like Landsat 8, unfortunately, has a return interval of about 16 days. And several models themselves need a minimum of about 3 observations to detect change. So that's 48 days in total. Now, there are multiple Landsat sensors, so we can combine them, but they are still optical, so clouds are still bad. Plus, they can only sense moderately large deforestation events, which doesn't help when we're trying to detect smaller scale. Now, we should point out, Ali can get really good maps of what's happened in the past, but that doesn't help them find out deforestation that's happening right now on the ground. So one of the main solutions to this limitation is to simply use data from multiple sources. Now, in remote sensing, data from disparate sensors can be either fused to make synthetic imagery or harmonized. Now, these multi-source approaches have recently become much more common, especially with the launch and subsequent open accessibility of data from the European Space Agency. So with the proliferation of accessible data and, crucially, freely accessible data, we are in the midst of a shift from retrospective mapping to monitoring, where we use all possible data in order to detect change in near real time, or as soon as it's happening. Now, some near real-time deforestation studies have shown very promising results, with detections decreasing from a few months to several days in the best scenarios. Now, Ali has seen all of this and decides to capitalize on the moment. And following trends in other studies, she decides she wants to try to use data from 3 sensors. Number 1, Landsat 8, like I mentioned before. The second is Sentinel-2, which is also optical, but at 10-meter resolution. And the final is our synthetic aperture radar, also at 10-meter resolution. But Ali is still running into 3 main problems. As mentioned, she has now access to multiple data streams, but she wants to find a solution that maximizes accuracy and latency, and then can easily combine the data sources. Second, the team has noticed that logging tends to use new roads, which are in flatter areas. But even though they can survey those areas, there's no way to add in that information to current models. And finally, Ali and the team can go out in the field and validate how well the model is performing, but they don't really have a lot of data, and it's also hard to get. So although they can see all of this, they can't use that data to then make the model better. In other words, once they have the model right now, its performance is static. So that's where we come in. We assert that correctly addressing these obstacles Ali is facing is crucial for having near real-time monitoring become more accurate and representative in order to most effectively help mitigate deforestation. So for my dissertation, we first created a novel detection algorithm designed to explicitly assess trade-offs between latency and accuracy. Second, we expanded the method by incorporating landscape drivers into the algorithm using Bayesian methods. And finally, we further expanded the model by developing a continuously improving system whereby input from users is directly incorporated. So let's get to it. Now, first of all, this research takes place in Myanmar, as it's one of the most forested countries in Southeast Asia. However, deforestation rates have been increasing, and they've been very high for a number of recent years, which is threatening endangered habitats and biodiversity. Now, we focused our efforts in the northern half of the country because it has the largest concentration of intact forests, and it has a good representation of other forest types. Now, within the study region, we identified examples of deforestation in the year 2019 using planet data, which has 3-meter resolution imagery, but it is not freely available. So we could use it only for the training data. Now here we identified 2 kinds of training. First, disturbances in the exact date of the event. And second, a control point nearby that wasn't deforested in the full study timeframe from 2015 to 2019. Now with these points, we can identify deforestation using the change in greenness, as I showed earlier. So let's look at an example time series from one of these points. Now, with time series change detection analysis, we look for 2 things. Are observations anomalous, and are they persistently so? Now, I need to introduce a couple terms. The line here is, of course, a harmonic time series model. And a residual is a positive or negative difference from each point to the fitted line. So here, of course, B is the larger negative residual than A is. So we then standardize or scale those residuals to have a mean of 0, and that's called a z-score. Now, good model fits with no deforestation, like in the beginning of this time frame, have their z-scores clustered around 0, which you can see here. Okay, so as we discussed, Ali wants to see change detection in near real time, and they want to use multiple sensors. So we can combine the 3 that we talked about using a simple harmonization process. And this, for example, is from the Landsat 8 sensor. And onto that, we can add Sentinel-2. And in Myanmar, we have a distinct monsoon season during which we get little usable data for the optical sensors. And this is where that SAR data with Sentinel-1 comes in real handy. So this looks great, right? We have like a cohesive time series. So why was Ali concerned about getting both the most accurate and the quickest alerts? Well, to illustrate the problem, I'll use a picture of a tortoise and a hare. So let's look at the z-scores from another training point. Now here, if we use a fast detector, we'd be super optimistic about each new observation's accuracy and probably label these observations as disturbances. But as you can see, they are anomalous, yet short-lived. However, if we use a slow detector, we'd be more conservative in our optimism and probably not label a disturbance until we had clearly persistent anomalies. In other words, our goal is to find a solution where we can detect deforestation both as quickly as possible and as accurately as possible. Unfortunately, some studies have looked into this already, and they were not able to find a solution. So our first chapter aimed to push the limits of deforestation monitoring and see if we can do these 3 things. First, detect disturbances with a new near real-time multi-source approach. Second, determine if Sentinel-1 is actually going to be useful here. And 3, fully characterize those trade-offs between latency and accuracy. And on top of all of this, we wanted to push the envelope of current remote sensing methods by trying to find small disturbances in a monsoon-dominated system and with a short training period, because we love what we do. So we therefore created a monitoring system from the ground up, where briefly we fit our harmonic or mean time series models of greenness for the optical sensors and a radar backscatter model for the SAR data, which you can see on the bottom here. We then calculated the z-scores and combined those into a single time series using just a simple harmonization method, as I said earlier. Now, after that, we took the z-scores and applied an exponentially weighted moving average to smooth that time series before finally converting that to a probability of disturbance. Now, there are a few ways to customize the algorithm, and so we tested multiple parameterizations to understand how latency and accuracy are affected by that. Now, one of those tests was how smooth we wanted the ZUMA, or the z-score exponentially weighted moving average, to be. And so, for example, a super smooth weighting where a lambda is that parameter that you can change. So a lambda of 0.1 can help avoid false detections, for example, here, but at the expense of fast detections. Now, you can really see that difference when we compare to a higher lambda, which is much more sensitive to each z-score magnitude. So on top of that, we also tested if having Sentinel-1 using that SAR data could help improve our accuracy metrics compared to just using the optical. Now, for our results, we first assessed trade-offs and then focused on using probability instead of just binary alerts. So we first quantified the trade-offs using the F1 score, which is just a balance of accuracies. And here that's on the y-axis. Now, this is great for retrospective mapping, but with near real time, we're focused on timeliness, which means we care more about how things change on a daily or observational basis. And so here on the x-axis, we're looking at days. So a lower lambda, or the smoother estimates, as you can see, have worse F1 scores immediately post-disturbance, but they eventually become some of the highest. Meanwhile, the highest lambda, or the most sensitive, starts with the best F1 score, but lose relative accuracy over time. Second, we analyzed the effect of including Sentinel-1 data, which we thought would help. Unfortunately, we didn't really find that as much. Now, obviously, the best F1 scores here are still roughly equivalent, but there's a much larger spread in those metrics over time. Now, clearly, though, including this SAR data does show a better example of that trade-off, where the conservative weighting, or the tortoise and purple line, are very clearly the top performing models at the end. But we do believe that SAR data in general doesn't help as much because the individual time series of SAR data are just much noisier than you get from the optical data. So, and that can lead to bad model fits. So let's talk about our use of probabilities now. To indicate disturbance, most methods use binary alerts that are generally produced with each new sensor observation. So you can say deforestation happened or it didn't. Now, though helpful, these alerts can obscure more fine-scale landscape dynamics in that a binary alert of 1 can technically mean anything from 50 to 100%. So we believe using probabilities can be more helpful because it gives users like Ali more information to work with, which can help with decision-making and more effective resource allocation. So let's look at what this can mean at a landscape scale, because so far we've been looking all at training data, but now we want to actually apply this over a large area. Because there's no optimal parameterization for the lambda, we use only our optical sensors, and we just chose an example lambda to do for an application. So specifically, we defined 2 subregions to see how the model performed over different forest types. Now here, each subregion is 10-meter resolution and about 5.9 million pixels in total size. So when applying at a landscape scale, we were able to create a daily time series of probabilities for that landscape, allowing us to see how deforestation events can actually grow per day, even at a per pixel level. Now here, the black areas, I should tell you, are non-forested or less than 30% canopy cover, and gray is anything that's less than 50%. So overall, we created a new algorithm that does the simple harmonization at landscape scale, and with our example parameterization, we can get a median detection time of 3 to 5 days with relatively high accuracy. And so we think this looks pretty good. Ali does too. Now, moving on to Ali's second problem. As we mentioned, her team has noticed deforestation tends to occur in flatter areas with roads, but she has no way of actually using this information in that model. So with our new method here, we can now try to address her concern. Now, change detection with remote sensing is really good at telling us where and when deforestation is happening, but it doesn't tell us anything about the why. Now, there's a large breadth of literature focusing on why deforestation occurs by identifying the direct agents and proximate drivers. But proximate drivers of deforestation from things like elevation and slope, where we'd assume, for example, deforestation would not occur at higher elevations and it would not occur really at like super steep slopes. Similarly, roads can act as transit corridors for logging, which is a big problem in tropical systems. And also, we'd assume the expansion of commercial agriculture and mining, for example, which can be financially important for local and regional interests, would further drive deforestation. But honestly, we don't need to randomly assume any of this. There have been many studies identifying drivers of tropical deforestation, and the majority have directly confirmed our assumptions. But because collecting data on drivers can take a long time, most research here is always conducted post hoc. It happens after the deforestation event took place. And so the exact combination of their agents and the magnitude also varies place to place. So we wanted to see if we can improve then our remote sensing-based probabilities of deforestation by incorporating some of these direct agents representing landscape dynamics into this near real-time system. Now, agents here were identified based on both surveyed literature and what was easily quantifiable from a remote sensing perspective. Now, for our presumption, we hypothesized that either the chance of deforestation would increase as the value of the agent increased, so directly proportional, or deforestation would decrease as the value of the agent increased. So for example, a higher elevation and a steeper slope, we presumed, would lead to a lower chance of deforestation. So to incorporate these with the remote sensing probabilities, we wanted to get an accurate representation of how these covariates varied across the landscape. So in chapter 1, we did a pixel-based analysis where each pixel or training point was processed individually and accuracy metrics were aggregated over all of them. Now, in chapter 2, we're focused on how spatial patterns affect our results. So we need a lot more training data. And for that, we used the global forest change data set to identify presence and absence of disturbance. We randomly sampled points for each year of the time frame used in chapter 1, and here the colors refer to that, where absence is 0, absence is 0 here, and the presence is a specific year from 2015 to 2019. We also sampled to reflect the average presence of deforestation across the landscape, which according to this global forest change data set was around 10%. So in total, we had 30,000 absence and 3,000 presence evenly split across those 5 years. So using those sample points, we set up a logistic model whereby deforestation, either it happened or it didn't, was related to different covariates we identified earlier. Now, even though our sample points were randomly chosen, there may still be a spatial pattern between them, and so we tested for spatial autocorrelation, and lo and behold, we do have it. And so we did need to account for that when we were building this model. Thus, we used the Bayesian integrated nested Laplace approximation method in R, or INLA, to quickly model the large spatial area, especially with that codependency. And to illustrate what that does, it basically makes a spatial arrangement of the sample points using a mesh of those spatial relationships. So our full model run gave us these results, and I'll walk us through it. Now, each covariate has a mean value, which is that point, and a credible interval, which is the most likely range of that effect. Now, we're looking at 3 primary things here. Number 1, what is the sign of the effect? Does the effect cross 0? And then what is the actual magnitude of those effects? Now, we'll look at a sample one here. Distance to previous disturbance has a negative effect, which, similar to what we had guessed, means that the chance of deforestation decreases as your distance increases. It also doesn't cross 0, which means we take it to be significant. In other words, high likelihood that the data was not observed by chance. And finally, the magnitude is relatively large, which means that distance to previous disturbance has a larger influence compared to these other covariates on the chance of deforestation occurring. Now, note we say a relative effect here because each of these covariates has very different scales, and so we had to standardize all of these before actually running the model. So we then ran a final model with only the significant covariates, and it gave us these results, which you can see in blue. So overall, our hypotheses held, but we did miss a signal for population density. And this could be due to a number of reasons, but one could be that commercial agriculture, for example, may occur farther from larger settlements. So with this final model, we can predict a chance of deforestation across the landscape, which we call prior probabilities because they represent here the prior knowledge of landscape dynamics. Now, this map here is from one of our subregions in chapter 1, and you can see how the low probabilities are primarily clustered within this wildlife sanctuary, with higher probabilities mainly on the edges. Now, as a reminder, gray here is non-forest or less than 30% canopy cover. So we now want to combine our original daily probabilities with these priors. And to do so, we just ended up using Bayes' theorem outright, which is an equation that essentially determines conditional probability. Now, in other words, our final estimation is based on a balance of these two data sets, but we also can vary the weight of evidence based on the data source itself. So let's look at those results. We confirm the trade-off we saw in chapter 1, where smoother weighting schema took longer to be accurate, but eventually became the most accurate. Second, our accuracy was roughly equivalent to chapter 1, where even though the Bayesian results did not peak as quickly, they did have higher peak F1 scores at the end of the monitoring window. And finally, we had promising results at a landscape scale, but first a short explanation as to why. Now let's take a simulated example here. A disturbance occurs at timestamp of x equals 81. Now in chapter 1, we only use remote sensing data to make this into a probability of disturbance, for example. In chapter 2, we then bring in those prior probabilities, which heavily affects the final posterior probabilities. And this can impact our interpretation of the landscape when, for example, we have predominantly lower priors. Now, this area is a wildlife sanctuary, as I mentioned, which helps explain the prevalence of those low priors. However, in this particular area, we also have a number of mist cloud detections and false positives from relatively dry conditions because this is in a tropical dry forested area. So how do we compare this with chapter 1? Well, we simulated a validation similar to what a team like Ali would be going to do. So we pretended we could go out into the field roughly 5 times a year and double check pixels that the model said were indeed deforested and record if the model was correct. Now, each time we checked 30 pixels, so in total, we had about 150 for the year. Now, we did this validation for the same pixels using the outputs of both chapters 1 and 2. And we found contrasting results between the two subregions. Oh, and there's your team again. Now, in this region, the spatial Bayesian method helped us rise from a true positive rate of 14 to 82%. And you may be saying, what the heck happened in chapter 1 for a 14%? And the reason is because the low priors, or at least our increase, the low priors helped us avoid all those false detections from the drier conditions and from clouds. It turns out trying to find NDVI, a difference in NDVI when something is brown and less brown is much harder than you think. Meanwhile, in the other region, we improved from about 76 to 79%. And this improvement was a lot smaller because there weren't as many initial errors, and it's a different forest type. This region 2 is much more coniferous, for example, and so a wetter forest overall. So overall, in this chapter, we have a few main outcomes. First, while previous studies have used remote sensing data to help identify deforestation drivers, this is one of the first studies to combine covariate information into a near real-time environment, and we use the INLA method to do so. Next, we confirmed the presence of trade-offs between latency and accuracy, similar to chapter 1. And finally, we better characterize the process of deforestation across the study region. So this gives us a better indication of what's contributing to deforestation in the first place, which in addition to our updated probabilities and the confirmation of trade-offs, can help us generate more effective deforestation mitigation by, again, giving users as much helpful information as possible. So this is great. Let's go check back in with Ali. So it looks like so far we've been able to address 2 of her problems. As I said in chapter 1, we have the new algorithm. We can get the latency and accuracy, some kind of optimization between them, but not truly. And for chapter 2 now, we've introduced a method that helps us better understand those processes, and it can help us identify why deforestation is occurring. So the final problem now lies with field validation. Now, as a reminder, Ali and her team are able to validate model performance, but they aren't able to go to the field regularly. And she's concerned because there's no way to update the model with the validation efforts. So using our method, we set out to help with this, and we developed an iterative validation approach whereby field validation data is directly used to update the probabilities, which in turn updates future probability estimates. So I'll explain this more. Now the system looks like this. We first generate the probabilities, then we go out and do field validation, and then we can use that data to update the original equation, regenerate probabilities, and then calculate F1 scores. And finally, we just simply repeat this pattern for each validation as we go until eventually the F1 score stabilizes or we change something else. So I'll show you an example of what this looks like. So from chapter 1, we have our training data and we have our two subregions. So what if we wanted to try our method in a new area that we haven't been to? For example, this one. Well, it's simple. We just say that we're going to work with uninformative prior distributions of the landscape dynamics. So I'll elaborate on that. And for chapter 1, for example, we have our Zuma values for the training data. Now, all of our values in the stable period, so before the deforestation occurred, we call D0. Meanwhile, the Zuma values post-disturbance, we call D1. And I note that we don't include all the post-disturbance values here because we want to avoid signals from potential regrowth like this. So then when we collate all of those D0s and D1s across all of the training data, we can build true distributions of what the values can be. And here we would call this light blue line a fully informative prior distribution. Now, if we use training data from a nearby region with, but not this one, we can call it semi-informative. And of course, we can also use no training data and have an entirely uninformative distribution like this. Now, what this uninformative means is that a Zuma value has an equal likelihood of belonging to either D0 or D1. In other words, undisturbed or disturbed. And you can see this on the plots where the dark line, that uninformative line, is symmetric around 0 for both D0 and D1, whereas the light blue line, which is a fully informative, for the D1 plot on the bottom has a definite negative lean. So because we're in a completely new area, we're going to use that uninformative distribution. So first, we calculate the probabilities from the algorithm using an initial distribution of the data. We then go out and do field validation. And because we're simulating this, our true values are just being drawn from a fully informative distribution. And then that data is used to update the original distributions to get a more accurate probability calculation and regenerate them. So this is a lot of words, but essentially what we want to do is that the distributions can become better over time. With every new validation event that you go out and do, even if you start with a fully uninformative distribution, they will eventually get to what you want or what you hope to get. So now when we get this new data, we can do one of two things. We can either add it into the system cumulatively, where you retain all of the data, both old and new, or adaptively, where you keep the same amount of data and you just replace the older data with the newer data. So we can then calculate our F1 score, which will continuously increase, of course, as we add more validated data to the system. And we just simply repeat this cycle until your F1 scores stabilize. So let's inspect our actual results here. Now, clearly, as we conduct more field validations and add more true data back into the system, we will increase our accuracy or that F1 score over time. Now, this is great, but as you can see here, it still takes about 70 validation events to get a stable accuracy. And that's more than once a week for an entire year, which can be difficult to do because of financial interests or weather. And Ali has already pointed out her team just can't do it. So we explored some small alternatives. For example, in this original setting, we said that for each validation event, we verified the state of 30 pixels. If we increase that to 50, we can reach that same accuracy, that stabilization, roughly 30 validation events earlier. So we ran a number of tests looking at the different parameterizations here, and we determined three main results. Number one, the more validation points you can get, as you might imagine, the faster you can increase your accuracy. Second, we showed that in an example with uninformative prior distribution. But if you start with any kind of somewhat informative distribution, the data is going to be more helpful. And finally, an adaptive approach where we replace the original data with that new data is better than the cumulative approach where we simply just add the data as it comes in. Okay, so we can clearly see that the algorithm can improve, but what does this mean for Ali and her team? Well, it means that even with the few resources they have, together they can customize the system and conduct field validation as they're able, with the knowledge that their efforts will help the model improve over time. Now, importantly, with this method, Ali and the team don't need many validation events to maximize the F1 score, especially with that adaptive incorporation. Plus, instead of being only the data users, they can now become their own data producers who maintain and improve the system on their own instead of relying on external people like me, who's not even in the system and lives far away and, yeah, isn't there. And so with all of that, we have addressed Ali's three main obstacles. First, she wanted to do that multi-source near real-time detection that could optimize latency and accuracy. And so we developed this algorithm from the ground up that tests that spectrum of trade-offs, achieves fast detections with high accuracy, and creates a daily probability time series at landscape scale. The second that she wanted to do, she suspected there were the landscape agents that were tied to deforestation, but you can't put that into the model. And so we developed a spatial extension of chapter 1 where we modeled the spatial autocorrelation, explored how deforestation was influenced by these different drivers, and learned more about the process of deforestation in Myanmar as part of the process. And finally, Ali wanted a way to make sure the few field validations that she and her team could do would be worth it. And so we developed a system where we incorporated field experts into the loop by building an iterative validation method that continuously improves even in areas where we don't have a lot of data and is customizable by the users. Now, it's important to note that this method is technically adaptable to any existing near real-time method and can help in other situations where validation data is difficult to obtain. And I just want to point out that we did everything with NDVI here, but because you're basically combining unitless data together for that data harmonization, you can use any kind of spectral index that you want or multispectral index that you want. We just use NDVI because it's one of the most common and it was also simple to do here. And maybe most importantly on all of this, we've helped to ensure the preservation of Ali's protected systems for generations to come. So that's the end of the PhD research, and I just want to acknowledge my committee doctors Josh Gray, Aaron Sills, Morella Tilbury, Roland Case, all at North Carolina State, and Grant Connett, who is at the Smithsonian. And I need to acknowledge also my funding, North Carolina Space Grant, a NASA Finance Grant, and United States Geospatial Intelligence Foundation. So that's the PhD, but I'm now going to pivot briefly to get to that bonus lightning content. And I'll briefly discuss what I'm working on here at Cary. So I'm now using my experience with change detection to help inform lightning research. And specifically, we're looking at how lightning affects tropical forest biodiversity using sensors and drones. So when a lightning strike hits, we have sensors that can record the electromagnetic pulse as it spreads out from the strike. And that's fine for detecting the intensity of a strike, but we want to know exactly where that strike occurred. Now, to do that, we need at least 3 sensors for triangulation of those coordinates. But more is always better as well, especially because our precision can increase with each new sensor added. Now, once we have the strike location, we can then go out to the field and try to find the tree from the forest floor, which is much harder than you think it is. I did not think it would be that hard. And once we find it, we can then try to assess the tree and the local area, and then try to record data about how the strike affected that local forest patch and its immediate surroundings. Now, this can help us understand mortality, especially of larger trees. Now, we can then take a number of these validated strikes and then extrapolate to a larger region, such as across central Panama, which can be tens of thousands of strikes every year. Now, all of this gives us a better picture of how lightning can drive carbon turnover in tropical forests. Now, it's worth mentioning also that this type of research has not been done before. Lightning has been extensively studied, but generally vis-a-vis fires, especially in temperate regions. But there's been relatively little research looking at its effects in tropical forests, and especially looking at explicit measures of disturbance intensity. So, in addition to lightning sensors, we are using drones to also identify gaps in forest canopy, potentially from lightning strikes as well. Now, to do this, we have a drone, shocker, that flies over our study area, taking a ton of pictures, just simple RGB. And we can then use PPK, or post-processing kinematic, as a GPS method from a base station that we can then accurately encode. And this is great because it means using PPK, as opposed to RTK, if you know what that is, real-time kinematic. These two don't need to be connected the whole time that the drone is in the air. Previously, they did, and so if your drone is flying far away, it can be difficult to sometimes get that GPS information. We now don't have that problem. So we have a video from a recent drone flight. It is short, but you can get an example of what this is like. And I will just like to point out that we are in the boat here controlling the drone in order to make sure that we still have signal as it goes all the way across the island. So one fun thing about that is that you might have seen where the drone kind of drops a little bit. It's transferring from, or it's transitioning from a fixed or multi-rotor mode, which it uses to rise up, to a fixed wing, which is what most drones normally use. When it does that transition, it does lose altitude because it's turning off those propellers. And the first time that it happened, all of us thought the drone was about to crash. So we were very glad that it didn't. So using a total of 4 flights across the entire island, we can then run 2 separate analyses on the data, or really the RGB pictures that we get from the drone. Whoops, there we go. Now for a structural analysis, we can build a point cloud from all of these images taken at different angles, and we can get structural information for canopy gaps, such as depth and area. We can then verify these using the drone images and actually go out into the field. Now, for example, this is a gap that occurred between March and June of this year. And you can clearly see in the June image, the fallen tree right there. It's kind of grainy, but you can clearly see it. And what's great about this is that we can further verify and look at a time series of this particular gap location over previous years. Now we can do the same kind of comparison, but then only looking at the spectral information. So instead of stopping at a point cloud, for example, we can build an orthomosaic from the images, which can look like this. Now with the new drone that we have, we can get a pixel resolution of 7 centimeters, which allows us to have really clear images at super fine scales. So from this, we can calculate a spectral index that highlights gaps and compare the current and previous flights. And so, for example, here you can clearly see some defoliated crowns from summer 2023 compared to summer 2022. So I just highlighted a couple of them there. Now, similar to what I did with the PhD research, you just use a spectral index to then difference the 2 images. So here we just took the summer 23, summer 22, calculate an index for both of them, difference the 2, and then you get something like this, where you can clearly see how the defoliated crowns in the 2023 image show up here as the darker colors. So overall, and then, we can then get this exact same area and depth, but it's a different kind of gap metric, but you can get the area, perimeter, and the location for these just as you can get that from the point cloud. So overall, we have our 2 processing pipelines where we both have the structural and the spectral information derived from drone photogrammetry. So that means in total, we can not only get an absolute quantification of lightning-caused disturbance, but also cross-reference that data with the drone and ground surveys to get the total contributions of lightning to tropical forest turnover across different age classes. So with that, I'm happy to take any questions, and thank you for listening. Sure.
Air first to do the early estimates and then put into a model that incorporates the tortoise and the better accuracy. Is that not the
Yeah. The question was, when I was talking about the tortoise and the hare, is can we, you said run the tortoise first?
Well, run one first. very short term. Investigating
So the question is, with the tortoise and the hare, can we run one first, for example, get the best accuracy first, and then at the end of the time frame, run the other one? I mean, in theory, yes. It's not it's not something we tried. It's a good idea. Yeah, if I had more time to think about it, I think I can give you a much better answer than in theory, yes. But it's a very good idea. Okay, thank you. July.
Question about the iterative validation portion.
Sure.
So, what could tell the situation that you were in a scenario where the team was just doing a binary check of like, was this place really deforested or was it not? And I've done iterative validation work myself before, and usually, I try to validate something a little more, fine grained than just the 0 or 1. Is it correct or is it not? So I kind of wonder whether you can improve the performance of the validation if you had a finer metric that was being, collected in the field, like say percentage deforested or something that's a little, finer grained than just is it deforested or not. And I wonder if that would help with kind of person power in the field, if you were taking, like if you could have fewer trips out to the field and still get accuracy if you were taking a metric that was a little more tailored.
The question was for the validation events, would it have been better help if we had done an actual, like similar to the probabilities we were talking about earlier, like a 0 to 100% type of thing, instead of just binary alerts or binary, like, yes, this place was deforested or not. Yeah, I'm sure it would, and it would probably actually improve the graphs of how quickly things change over time, like similar to what I was showing here. I think if this were like a true field, like actual operational thing, which initially I had wanted to do, but it's a lot harder to do that in a PhD. I think, yeah, that definitely would have been something that we incorporated later. Sure. Yes. So the question is how sensitive is our approach for the PhD research to selective logging, and can we measure recovery from it? We discussed, my advisor and I discussed both of those things when we were developing this. The answer to the first part is that for the selective logging, that was the initial goal. Ultimately, we are completely limited by the smallest scale remote sensing data that we're using. In this case, it is the 10-meter Sentinel-2 imagery. Now, 10-meter is not, it's not terrible, but ultimately we're still confined to where we need at least, because in order to see that signal in the data, you need at least like 50% clear cut over that pixel, for example. So true selective logging, which I don't even know if there's a definition for that, but I'm thinking like take a tree here, take a tree here. If the canopies were not large, then I think it'd be a lot harder to see. As for recovery, we had talked about initially incorporating that into the workflow as well. But the amount of time that it took us just to spin up the original model, we quickly realized that that would be something for, in the future. But we wanted to, but yeah.
We have a question online that's somewhat related, so I think I'll get to that quickly. Ricardo Dalagnol asked, we said, great presentation, Ian. He wanted to know, did you also explore the minimum mapping unit for your experiments? And what would be the minimum deforested area you mapped in Myanmar using the combined Landsat and Sentinel data?
Yes. So in theory, so similar to what I mentioned for Sarah's question, the 10-meter pixel is what we technically use, so 100 meters squared is what we technically use as our minimum mapping unit, because we were using each pixel, like the analysis was run over each pixel individually and then blasting it onto a high-powered computer. So it goes through all of it. And we found that in that scenario, like with looking at that GIF over time at the end, it seemed to be doing the job. The problem, though, is obviously we weren't able to, I couldn't go out into the field to validate any of this because of both COVID and the military coup that occurred in Myanmar while I was doing my research. But the numbers, the exact numbers, Ricardo, that you're talking about, it's a good point. Thank you for bringing it up. It's something that it's something that needs to be done in terms of figuring that out, especially for how usable is a method like this later. And it's a question, I know that when we were looking at different papers, this is something that everybody brings up in their own change detection analysis. What is that minimum mapping unit? So at short, I can tell you 10 meters squared. But yeah. Go ahead.
So great talk. It was really fun to see. I had two questions kind of bubbling with excitement from the presentation. So the first is, what is the potential to use a multi-sensor fusion approach to get at agent attribution? So, there's lots of disturbance agents that cause deforestation. Can we get to actually figuring out what the agents are? And then second, the work is all done at, at pretty small landscapes. How does this scale computationally to larger domains? Like, could we do all the Amazon? Could we do all the planet?
I'll answer the second question first, which was how well could this be scaled up computationally, for example, like all the Amazon or the planet? In theory, you're just limited by computing power. In terms of the specific, like how long that would take, at 10-meter resolution, for Myanmar, for this kind of scale, this took, on a high-powered computer, not maximizing what I had, but running it relatively, I could get the whole process done in 5 hours, pretty sure. So in theory, my lab mate did something like this, and it took him, he ran it for like 2 weeks, 16,000 or 16 million jobs, but he got it done. So really, the reason why I focused here was just to make it more feasible for the PhD itself. Your first question was about, can you repeat it, please?
Sorry, agent attribution.
Yeah. Okay. This first question is about agent attribution using the multi-sensor approach. So it's a good point. I think it can be done. I think it should be done. Because like I said, still, even like when I was researching this, I was like, there's got to be someone must have done some kind of agent attribution in a scenario that's not like, oh, this happened 10 years, 12 years in the past. Okay, we're going to now look at that. I just couldn't find it. And maybe it's because I was really searching for Myanmar specifically, but I looked at both global and local, and I just couldn't find it. So I want to say the answer is yes. It seems like it should be possible, but I haven't seen so far anybody else who has actually tried to go in and do that. It's up to you.
Yeah.
In the Myanmar deforestation study, it looked like it went by really quickly that there was no effect of distance to roads, either main roads or deep roads. Is that really what was there? And so, how would you explain that?
I think this is it. Yes. So the question is, it seems like there's not really that much of an effect of distance to roads. And why would that be? So part of the reason, I think, is because we use three kinds of, well, initially I was looking at three kinds of road shape files that essentially we use for the model. What we found, and these are two of them here. So main roads is, as you can imagine, all roads includes like your smaller road. As far as I know, it also includes dirt roads throughout Myanmar. And the reason for the roads, I was kind of surprised. I had expected, as you said, I had expected more of a definite, like it's either a positive or negative lean. I don't have it off the top of my head right now. I know we put it in the paper, or at least in the second chapter. But I know we had a good reason, and I'm really sad I can't think of it right now. But I can get back to you on that.
Jane, I think you had a question.
It's a pretty simple-ish question, I think, but I'm just curious. There's all these efforts to increase our like satellite imagery and this style of integration. I'm curious what you feel is if we only had better this would all be an easier process. So like, is it we need finer scale data, or we need finer scale time points, or we need a different spectrum? Like, I'm curious what would make this easier and more accurate?
So the question was, what is the one thing that I can think of that would make this research easier and more accurate? The shortest answer is an actual disturbance data set. If I didn't have to get all of this myself manually, this would have been, I could have maybe gone into a bunch of the other stuff that other people have talked about, recovery or agent-based attribution and all that. There is no disturbance data set, as far as I know, that is currently out there available and gives you the coordinates of a disturbance and the exact day that it happened. It just does not exist at that kind of scale, which is infuriating because it seems so simple, and I just could not find it. The people who have that data, maybe they have shared it. If they have, I don't know about it, but I think a lot of them are sitting on it. And I know personally, I'm going to publish this data set when the paper is published, but it's not that big. So that would probably be the best thing. The second best thing, honestly, we need something like Planet that's free. 3-meter resolution. It'd be better if we had better. I mean, honestly, if we had 7-centimeter resolution for the entire globe, that would also be great too. But then the memory is massive. So
I had one follow-up question also. So you mentioned some limited utility of adding the SAR data in, and some of that's related to the noise that exists. And I'm curious about the spatial distribution or spatial variation of that noise. I would guess there are potentially some places where it's more or less noisy. Do you think in the places where SAR data are inherently less noisy, it might be related to slope or whatever it is, that it might actually be more useful in the model? And is that something that you looked at all?
Yes. Well, so SAR is an interesting thing. And I'm just going back to the slide so I can show you that. So SAR data, as I mentioned here, it's this simplest explanation of what it is that the data it sends out data actively, and then it bounces back and hits the sensor. There are different, and one thing that I said when I was going through this slide is that we tend to look at SAR data with longer wavelengths. And what that actually means is that there are different, they call them by letters. There's C-band, Ku, Ka, X-band, L-band, SAR. C-band is what happens, especially with forests, we call it volume scattering. And so what happens, so if, for example, if you have this plant here, C-band is going to come down, bounce around a little bit here, and then get shot back. If you have longer wavelengths, it'll actually go through that more. And L-band, for example, which hasn't been launched yet, which was supposed to launch in 2020, L-band will go through here. It will penetrate much further into the canopy before then bouncing back. And so the noise question is, it's more related to what the ground cover is than anything else. And so, and the problem with the deforestation stuff, especially if I cut this tree down, but I leave the logs there for a couple days, C-band SAR is going to give me a very similar signal to what it was if the tree was still there. Similarly, if you cut this down, take away the logs, and then you have some kind of cover crop come up in its place, as long as it's above, like, I don't know, if it's knee height or something like that, C-band SAR will give me a similar signal as if it was never cut down in the first place, because it just doesn't penetrate that much farther. So that's the reality of using SAR data. And I don't remember exactly what your final question was.
Oh, I think you answered. It was just about
Okay.
if it varies over space, if you would use the less variable sections, but it sounds like it's noisy everywhere.
Yes, we had wanted to use L-band SAR. That was in the original proposal when I proposed this because it was supposed to launch within a year of me writing the proposal. And now it still hasn't launched yet.
Yeah.
Or it has. It's very close, but yeah.
Great. Well, thank you for the great presentation, Ian, and thank you everybody for attending. Again, there will be lunch right after this here in the lunchroom, and then happy hour at 4. So thank you.
Thank you.